Right. So, as I said, today's topic will be viscosity, which is basically, okay, as it is mentioned here, resistance to the flow of a fluid. So, it's like friction between fluid layers. Okay. Uh, can you tell me, Aishwarya, what is the difference between the flow of water and the flow of a thicker liquid, let's say honey? Okay. What's the difference between the way they flow?
So
What
the speed.
speed? Okay. Basically, the ease of flow. Water can flow very easily. Honey doesn't flow that freely. Okay. So basically, honey is more viscous than water. Okay. It's difficult for honey to flow compared to water. More difficult. Okay. So that is what is viscosity. What we are going to do is we'll study uh, the factors on which viscosity depends. Fine. We'll derive an expression for viscous force. When an object moves through a fluid, okay, it experiences a resistive force called viscous force. We'll write an expression for it and we'll solve some problems based on it. Okay. But before we get into viscosity and all, we need to discuss one type of flow called laminar flow. Okay. Now, suppose this fluid is flowing on this surface. Okay. You assume water flowing on a surface itself. Okay. Now, we call the flow as laminar flow if it flows in the form of layers. Like the first set of molecules which is in contact with the surface is one layer. The next set of molecules is another layer. Okay. The third set is another layer and so on. Okay. Flow in this form is what we call as laminar flow. Lamina means sheet. Okay. So laminar flow means sheet like flow. Okay. Layers or sheets. So you can imagine them like a pack of cards also. Okay. Pack of cards, you just push the pack. What will happen? Each card will get displaced by a different amount, but all the molecules of one card will get displaced by the same amount. Okay. So it's something like that. So we call the flow as laminar flow if the fluid flows in the form of layers like this. Okay. You can even visualize it like this. Each layer must have a common velocity. All the molecules belonging to a certain layer must have a common velocity. Fine. That is when you call it as laminar flow. So each layer is like one set of molecules. It moves together. Next layer moves together. Third layer moves together. But layer to layer, the velocity can change. Okay, that is what is laminar flow. So basically, flow in the form of or fluid flow like sheets or layers is what you call as laminar flow. If that behavior is not there, then we call it as turbulent flow. Okay, so these are the two opposite types of flow you can say laminar flow and turbulent flow. Right. Along with laminar flow, there is another condition under which the equations we apply are applicable. Okay, the equations we study are applicable. The other condition is that no slide condition or the boundary layer condition. Basically, what it means. Suppose there is a fluid flowing like this on a flat surface. It can be flowing in a pipe, it can be flowing on any kind of surface. Okay, so see, no surface is perfectly smooth. Even if it's a surface of glass on which water is just dripping down, glass surface is also at the molecular level not perfectly smooth. So some roughness will be there. Now, due to roughness of the surface on which the fluid is flowing, okay, consider the surface being rough like this. Okay, just some at the molecular level, random roughness will be there. Okay. Now, the first set of fluid molecules which are in contact with the surface, what happens is the first set of molecules gets locked in those grooves. Okay. Gets locked in the roughness of that surface. As a result, what we assume, okay, it's not always true, but what we assume is that that first layer is relatively at rest. Relative to what? Relatively at rest with respect to the surface on which the liquid is flowing. Okay, this is called the boundary layer condition or the no slide condition. So the first layer does not slide at all with respect to the surface. The next layer, okay, the second layer of fluid can slide over the first layer. Okay, so first layer is at rest with respect to surface. Second layer can have some velocity. Okay. Now from first layer to second layer, there is some change in velocity. First layer is at rest. Second layer has a slightly higher velocity. So relative to first layer, second layer has some speed. Now relative to second layer, third layer can have some speed. So consider the third layer of fluid like this. With respect to second layer, third layer can be sliding. Means with respect to ground, if you see, third layer will have an even greater speed. For example, suppose the first layer is at rest. Okay. Rest means 0 meters per second. Let's say the next layer flows at 2 meters per second. So with respect to first layer, second layer has a relative velocity of 2 meter per second. Now with respect to second layer, third can have a relative velocity of 2 meter per second. That means its actual velocity becomes 4 meters per second. Like that. Okay. And as you go further away from the surface, the velocity of the layers goes on increasing. So this layer will have an even greater velocity. Like with respect to third layer, fourth layer will be sliding. So it will be moving faster than the third layer. Okay. And then the next fifth layer and so on. Okay. You can continue like that. So basically in laminar flow, if you apply the no slide condition or the boundary layer condition, you will get a velocity profile like this. Velocity profile or a velocity distribution. Okay. So as you move away from the surface, layer by layer, the speed will be increasing. That is the idea. You have to visualize the flow like that. Fine. So remember these two conditions. First is laminar flow, the flow of fluid in the form of layers. And when I say fluid, I'm including both gases and liquids. Viscosity is a property of gases as well as liquids. Surface tension, the last property that we discussed, is a property exclusively of liquids. Okay, gases don't exhibit surface tension, but gases exhibit viscosity. Okay. So as you move away from the surface, layer by layer, the velocity will be increasing. The speed will be increasing in case the fluid is flowing. So suppose you consider a circular pipe. Okay, just a moment. Right. So assume there is a viscous fluid flowing through this circular tube. Now, some fluid molecules will be in contact with the walls of the tube. We just discussed the boundary layer condition or the no slide condition. Okay, what does it state? I'll mention it here. The layer of molecules, okay, the layer of fluid molecules in contact with a surface must be at rest with respect to the surface. Fine. So the first layer of molecules which is in contact with the surface will be at rest. And as you move away from the surface, the velocity of layer will increase layer by layer. Okay. So keeping that point in mind, try to visualize the velocity profile of fluid layers in this case. Okay. Now, how will you visualize layers in this case? The surface of the tube is cylindrical. So layers also have to be considered cylindrical. Fine. So one cylindrical layer in contact with the wall of the tube. Next cylindrical layer slightly smaller than the first layer. Third cylindrical layer slightly smaller than the second layer, and so on. I want you all to imagine the velocity profile. Okay. What I mean is, consider fluid layers like this. Let's say this is one layer of the fluid. Right. So let's consider different layers of fluid flowing inside this tube. Now, the blue layer is the first layer, which is in contact with the tube. The green layer is the layer after it, then the yellow one, then the red one. And after that also you can imagine layers if you want. Now, based on the no slide condition, one of you tell me which of these layers will not be moving at all? Which of these fluid layers will not be moving at all? The fluid layer which is in contact with the surface should be at rest with respect to the surface. So, which layer will not be moving?
The blue. Yeah.
The blue one will not be moving. Okay. And you know that as you move away from the surface, the speed of layers increases. Speed of the layer increases. So, which layer will be moving the fastest? Which layer, which fluid layer will be moving the fastest? Vanilla unmuted, but we couldn't hear anything.
The red layer.
The red one. Okay. So you can visualize a velocity profile like this. The green layer will have small velocity. Next, the yellow layer will have a much larger velocity of flow. Next, the red layer will have an even larger velocity of flow, even greater velocity of flow. Right? You can maybe consider one more layer here, orange one. It will have the highest speed. Okay. So of all the layers or of all the molecules flowing through this tube, the molecules which are near the axis of the tube will be moving the fastest. Okay. All those molecules, you can imagine a set of molecules here, they will be moving the fastest. Okay. The set of molecules closer to the walls of the tube will be moving the slowest. Okay. So you can think of a velocity gradient or a velocity profile like this in laminar flow under the assumption that no slide condition is satisfied. Usually it is in real life situation also, no slide condition is obeyed. Means boundary layer condition is obeyed. The layer which is in contact with the surface will be at rest with respect to the surface. Okay. Next we shall discuss the expression for viscous force. Consider a viscous fluid like this. Can one of you tell me any material which floats on water? Just name a material which can easily float on water.
Wood, sir.
Wood. Hmm. Right. Okay. Plastic, wood. Fine. So suppose there is a thin sheet of plastic. Okay. Wood also you can take, nothing wrong in that. Like boat can move on water. Fine. Uh, Not all kinds of wood floats on water, but dry wood usually does float. Fine. So let's consider a polythene sheet, for example. Like you can try this in real life also. Assume there's a polythene sheet placed on water. Okay. The gray line indicates the polythene sheet. It's on water. Water in real life is a viscous fluid. Okay. Ideal fluids are non-viscous. We are talking about real fluids. Fine. Suppose you want to slide this polythene sheet on the surface of water. Okay. Polythene sheet or a thermocol sheet also you can consider. Let's say you want to slide it on the surface of water. Do you think it will be very easy to slide? Like you give it some velocity, it will keep sliding forever? Or do you think you will have to continue dragging it? If you want to make it continue sliding, do you have to continue dragging it? Or if you give it one velocity, it's enough? It will slide on its own. From real life experience, what do you think? You must have tried like pushing boats, paper boats on the surface of water, no? Like you give them some velocity, they won't continue moving on their own. Okay? If you want the boat to continue moving forward, you will have to apply some force. Why? Consider this. See, we considered a polythene sheet, okay, which is floating on water. The polythene sheet will have some roughness. Now, the topmost layer of water here is in contact with that polythene sheet. So when you drag that polythene sheet forward, okay, when you drag the sheet forward with a certain speed v, basically what you will have to do is you will have to drag the topmost layer also with the same speed v. Why? Boundary layer condition. Okay, the topmost layer is in contact with the polythene sheet. It's in contact with the surface. Relatively, they must be at rest. So if you want to drag the sheet, you'll have to drag that layer of water, okay, or the layer of fluid along with the sheet. So they will be going with equal velocities. Now the bottommost layer is at rest. Topmost layer has to move with the speed with which you want to move it. Bottommost layer is at rest. The other layers in between will have gradually decreasing velocities like this. So you will have to create this velocity profile in order to make that layer move. Fine. If you want to move that polythene sheet with a speed v, you will have to move all the fluid layers along with it like this. Not all fluid layers will move with the same speed. There will be a velocity gradient. Gradient means what? Generally, gradient of any quantity means the rate of variation of that quantity with distance. Okay. So here, as you move away from the surface, okay, like in this y direction, as you move, the velocity of layers is varying. Okay. So there is a certain rate at which velocity changes from layer to layer, dv by dy, or average rate of change. You can write delta v by delta y. This is what we call as velocity gradient. Okay. So if you want to move that sheet, polythene sheet, you'll have to develop this velocity gradient. Fine. Now, fluid layers, naturally, they have some friction between them. That is what is viscosity. So basically, what you will have to do is to continue moving the sheet with this velocity, you will need to apply a force which is enough to overcome the viscous force. Okay, the fluid layers will be resisting that movement. The force you apply should be equal to the viscous force. Okay, only then you can expect it to move with a constant velocity. If you apply force greater than viscous force, you can make it speed up. If you apply force less than viscous force, it will slow down naturally. Okay, but if the applied force is exactly equal to viscous force, then you can maintain a constant speed. Okay, now I don't know how many of you have tried pushing polythene sheets or plastic sheets or thermocol sheets on the surface of water, but if you try it, you will realize that greater the speed with which you want to move the sheet, greater will be the force with which you need to pull it. Okay. Now, the force with which you need to pull is basically equal to the viscous force to maintain a constant speed. Therefore, from everyday experience, what we can say is viscous force is proportional to the speed with which you want to pull that layer. Okay. Greater the speed with which you want to move it, greater the force you need to apply. Fine. Next, it is also proportional to the area of contact between that polythene sheet and the liquid. Okay, because whatever molecules of liquid or fluid are in contact with that polythene sheet, those molecules get dragged along with it. So larger the area of contact, greater the number of molecules you will have to drag. So that way we can justify why viscous force is proportional to area of contact. Okay. Next, uh, this some of you might have observed, like if you spill a few drops of water on a table, okay, consider this as a table surface. Spill a few drops of water. Imagine a few drops of water spilled on it here and there. And you put a sheet on it. Okay, it could be a paper also. Paper, plastic sheet, anything. And you try to drag the sheet, it will be very difficult. Not, okay, not very, very difficult, but it won't drag, it won't slide easily. Okay. If you try to pull this sheet sideways parallel to the table, there will be a significant resistance. Fine. It feels as if the sheet is stuck to the table and you will have to apply significant amount of force to slide it. Basically, what is happening there is viscous force is preventing the sliding of that sheet. Now, the same thing if you try in a bucket of water. Okay, assume there is a large container of water like this. You put that sheet, okay, plastic sheet or polythene sheet on this water, and here you try to drag it. Okay. In this case, you will see that it is relatively easy to slide the sheet than sliding it on the few drops of water spilt on a table. Okay. What does that mean? It means in this first case, the viscous force is higher than in the second case. What is the difference between the first case and the second case? The number of fluid layers. Okay. So basically, viscous force depends on this height y. Okay. And greater that distance, easier the flow will be. Okay. So it is inversely proportional to that height y. And obviously, viscous force depends on the fluid through which you are trying to move that object or fluid on which you are trying to move that sheet. So it depends on properties of the fluid as well. That property is called viscosity. Okay. So putting all these factors together, we get the expression for viscous force. Viscous force is equal to, okay, it's proportional to these three factors, right? It is proportional to speed with which you want to drag it, area of contact, and inversely proportional to distance between the, okay, what is y exactly? How do you express y or name y? Y is the separation between this first layer. First layer is the fixed layer, no? And this last layer. Last layer is the one with which you want to move. I mean, last layer is the layer which you want to move with the speed v. Fixed layer speed is 0. This layer speed is v. Okay. So y is basically the distance between those two layers. Okay. Now, the proportionality constant in this case is something called as coefficient of viscosity of the fluid. So we can write viscous force is equal to eta. Okay. Eta is the proportionality constant. A v divided by y. A more appropriate expression would be, like in this case, y is the distance between the layer which is at rest and the layer which is moving with speed v. Fine. Now, it's not necessary that you always know that distance, but v divided by y will be equal to delta v divided by delta y between any two layers. Okay. Relative speed between two layers divided by the relative separation between the layers. So an even better expression for viscous force would be eta A delta V divided by delta Y. Okay, what is delta V here? Relative speed between two fluid layers. If you take the first layer and the last layer, it becomes V minus 0, which is V. If you take any other two layers, it's V2 minus V1. Okay. Relative speed between two fluid layers. And delta Y is the separation between those two layers. That's all. Okay. Eta is called coefficient of viscosity, or sometimes they just call it viscosity of the fluid. Fine. Now you have the formula here in front of you. This is force, viscous force, okay, on a flat surface. Derive the SI unit and dimensional formula of coefficient of viscosity. Okay, this is important. Do this, all of you. So viscous force is eta A delta V by delta Y. Viscous force, okay, any force, the dimensional formula is ml t power minus 2 is equal to dimensions of eta multiplied with area. Area is L square. Delta V or V will have the same dimensions, L t power minus 1 divided by Y is a distance. Delta Y will also be a distance. L gets cancelled. 1 L can be cancelled. T power minus 1, T power minus 2 will be T power minus 1. Therefore, the dimensional formula of coefficient of viscosity becomes M. 1 L is cancelled, the other L goes to that side. L power minus 1, T power minus 1. Okay. So SI unit becomes kg per meter per second. Fine. Now you can also write it this way. F is equal to eta A delta V by delta Y. Right? So eta dimensions or eta units become force. Force is in newtons. Okay. Delta Y is a length, so meters divided by area will be in meter square. Velocity is in meters per second. Okay, meter cancel. Second goes to numerator. Newton per meter square. Force per unit area is pressure, Pascal. Okay, and second will be in the numerator. So this is also written as, or more commonly written as, Pascal second. Okay, this is the common SI unit for coefficient of viscosity. Right. Now, if you look at the CGS unit, this is also interesting because usually when you express in SI units, no, viscosity numerical value will be very small. It is better expressed in CGS units. Now, why do we have different units for the same quantity? Ease of expression. Okay. If you want to express the length of a pen or pencil, it will be convenient in centimeters. If you want to express the distance between two cities, it will be convenient in kilometers. Okay. So for convenience, we have different units. So if the measurement is small, smaller unit is better. If the measurement is large, larger unit is better to express. So it's important to know the CGS unit of viscosity as well. SI unit is kg per meter per second. No, CGS unit automatically becomes gram per centimeter per second. Okay. If you express this in terms of the SI unit, gram is what? 10 power minus 3 kg per centimeter. Centimeter is 10 power minus 2 meter. Okay. Second inverse, you can keep it as it is. So effectively, this becomes 10 power minus 1, means 0.1 kg per meter per second. So basically, CGS unit is 1/10 of the SI unit. It's a smaller unit. Okay. 0.1 times SI unit. SI unit is Pascal second, no? CGS unit has a separate name given to it. It's called poise. Is 0.1 Pascal second. This conversion is very important because in questions they usually give the viscosity in poise. Okay, but you will have to convert it to Pascal seconds, that is the SI unit, and then apply it in the equations. Okay, so remember this. Fine. Just a moment, I'll find out the viscosity of water. Right. The viscosity of water is approximately 1 millipascal second. Milli means 10 power minus 3. So it's approximately 10 power minus 3 Pascal seconds. If you express this in poise, it becomes 10 power minus 2 poise. Okay. Because 1 poise is 0.1 Pascal seconds. So 1 Pascal second becomes 10 poise. Okay. So in place of Pascal second, if you write 10 poise, 10 power minus 3 into 10 becomes 10 power minus 2 poise. It's still quite small if you can, as you can notice. Fine. Let's solve one problem based on this. Based on what? We have a formula now for viscous force exerted on a flat surface. Fine. In terms of what? In terms of coefficient of viscosity, area of contact between the object and the fluid, and relative speed between two fluid layers, and the separation between those two fluid layers. If you know these things, then you can tell the viscous force. Okay. So consider this. Consider a boat, okay, of floor area. How much shall we take? Approximately, let it be 20 square meters. Okay. Moving on water. Water viscosity we just discussed. 0. Okay. 10 power minus 3 Pascal seconds. Okay. In a lake of depth, let's say the depth of the lake is some, okay, 3 meters. Pond or lake you can consider. With a speed, how much shall we take? Maybe 2 meters per second. It's moving with that much speed. Okay. First thing, derive the viscous force acting on the boat. Next, to make the boat move with that, continue moving with that velocity, we will need to apply force. Okay. The one who is rowing the boat, or maybe if the boat has an engine, the engine will have to push water with that much force. Only then it can maintain that speed. So if you know the speed with which something is moving and you know the force that is acting on it, you can tell the power. So derive the power to be supplied to the boat to maintain that speed. Okay, solve this, both of you. I'll give you 2 minutes. Okay, I got one answer for the first part as 0.013. We'll see. Now, this boat is moving on a lake of water. Okay, now lake is basically a body of water which does not flow. Fine. So you can visualize it like this. Lake or pond you consider this way. And let's say there is a boat moving on that water. Depth of the lake and all are given to you. Okay. Now the boat has to move with a certain speed. So the top layer of water will have to move with that speed. Bottommost layer will be at rest, obviously. So you know the relative velocity between two layers and you know the depth of the lake. So you know the distance between the two layers as well. That's all. You directly apply the formula for viscous force. In this case, the formula is eta A delta V by delta Y. Eta is 10 power minus 3. The area of contact between the boat and water is 20 meters square. Difference in velocities between two layers. We know that the bottommost layer will be at rest. Topmost layer has to move along with the boat. Okay. So that will be 2 meters per second divided by the distance between those two layers is 3 meters. That's all. So 40 by 3, 13.33 into 10 power minus 3 newtons. That becomes 0.013. Fine. Fine. So that's the viscous force acting on the boat. And for the boat to continue moving with that speed, the engine should exert this much engine or the propeller should exert this much force on water in the opposite direction. Fine. So power delivered by the engine, we know power is F dot V. Okay. Force and velocity will be in the same direction. Then 13.3 into 10 power minus 3 and a boat is moving with speed 2 meters per second. So the power to be delivered is 26.6 or 26.7 into 10 power minus 3 watts. That's all. Okay, Aishwarya, is this clear? Any doubt in this? Fine. Consider a long vertical tube. Okay, you can think of it as a metal pipe itself. Fine. And assume that tube has some grease applied on it. Okay, or oil, grease or oil you can consider. Let's say oil is applied to the walls of that tube. Fine. Oil viscosity can be taken as eta. Now consider a cylinder, cylindrical object. Object's density is rho. Fine. Uh, the diameter of this cylindrical object, take it as, not diameter, the radius, take it as small r. And the radius of this long tube that is there, let's assume it is capital R. Obviously, capital R greater than small r. So the cylinder can fit inside that tube. And the length of this cylinder, let it be L. So if you know length and radius, you can tell its curved surface area and all those things. You can even tell its mass because you know the density as well. It's a solid cylinder. Okay. Now, this cylindrical object is placed inside that tube like this. Right? The gap between them is filled with the oil. Right? Now, based on your imagination, any of you can tell what will happen after this cylinder is released inside that long vertical tube. Vertical tube is stationary, fixed. Okay. If you release this cylinder, Inside that long vertical tube, what is going to happen? The cylinder is released from rest inside the long vertical tube. What will happen? Will it fall down or not? I mean, will it slide down or not?
Yes, sir.
Yes. Is the cylinder in contact with the oil or not? It
Yes.
is. It is. Okay. The curved surface of the cylinder is in contact with the oil. The oil is also in contact with the wall of the tube. Okay. Now, as this cylinder starts moving down due to gravity, what happens is the cylinder will drag the first layer of oil along with it. Okay. Boundary layer condition. The cylinder, the curved surface of the cylinder will be in contact with oil, no? So when the cylinder goes down, that first layer of oil will also have to go down with it. So you can imagine oil layers like this. Just a moment, I'll have to draw a diagram. Okay. So this layer is in contact with the cylinder. The innermost layer of oil is in contact with the cylinder. The outermost layer of oil is in contact with the pipe. Okay. Now the layer in contact with the pipe has to be at rest with respect to the pipe. The pipe is fixed, so that layer will be fixed. Cylinder falls inside the pipe. Because the cylinder falls inside the pipe, the layer of oil which is in contact with the cylinder will also have to go along with it, like this. As a result, what will happen? You will get a velocity profile of oil layers. Okay, different layers will be moving with different speeds. Situation will be like this, right? So if you observe, the layer moving along with the cylinder moves the fastest. The other layers move relatively slower. The last layer, the one which is in contact with the tube, will be at rest. So you'll be developing a velocity gradient like that. And layers are sliding over each other. So obviously there will be some viscous force. So once this cylinder is released, under the influence of its weight, it starts falling down. Initially, weight is the only force acting on it, mg. Under the influence of mg, it starts falling down. Okay, sliding vertically downward. But as it moves down, it will have to drag oil layers along with it. So viscous force will start acting in the upward direction on the cylinder. Okay, everywhere on the curved surface, it will be acting in the upward direction. That is viscous force. Now, viscous force, we just discussed the expression for it. Eta A delta V divided by delta Y. It depends on the velocity gradient that develops. Now you can see this is the velocity gradient. First layer is at rest. Last layer moves with the same speed with which the cylinder moves. Initially, cylinder was not moving. So initially, there's no velocity gradient. All layers were at rest. So there's no viscous force. But as the cylinder gains speed in the downward direction, this layer which is in contact with the cylinder moves faster and faster. Okay, so the velocity gradient increases. If velocity gradient gradually increases, viscous force also gradually increases. Then, as the cylinder continues falling down at one position, okay, or at some time, it will so happen that the weight of the cylinder mg is exactly balanced by viscous force acting on it in the upward direction. That situation will definitely arise because initially weight is dominating, no? So it will gain speed in the downward direction. As the cylinder gains speed in the downward direction, relative speed between fluid layers increases. And if relative speed between fluid layers, oil layers increases, the viscous force becomes stronger and stronger. So after falling by a certain distance, the weight will get balanced by the viscous force on this cylinder. Okay. Once weight is balanced by viscous force, net force becomes zero. Then it moves with a constant velocity. That velocity is called terminal velocity, but we'll use it later. We won't call it terminal velocity now. So I hope you understood the situation, what is going to happen with this cylinder. So what I want you to find out is the final speed of the cylinder. or the final speed with which the cylinder falls? Actually, if this question is asked in exam, no, they won't help you with that visualization. They'll just say cylinder is released inside this tube, find out the final velocity. Then you'll have to think, why will it have a fixed final velocity? Final velocity becoming fixed means finally force becoming zero, balancing. Which force will balance its weight? As the cylinder falls down, it will drag oil layers along with it. So viscous force must be balancing. All those ideas you will have to think. That is the difference between classroom and exam. Okay, and that is where most students fail also. In class, teacher will explain or simplify the situation, then it's very easy for you to solve. You know which topic is being discussed, you know which equation has to be applied. It's very easy for you to solve. But when you face this in exam, all that thinking has to be done on your own. Okay, so it's necessary that you keep solving problems. You have to get into the habit of solving problems on your own without assistance from the book or your teacher. Okay, practice questions every day. Right. So I want you to derive an expression for the final speed with which the cylinder falls. All the required information is given to you. Cylinder density is rho. Radius of the cylinder is small r. Length is L. Radius of the tube is capital R. Capital R is greater than small r. Okay. There's a significant difference between them. This is small r. From here to here is capital R. Okay. So in that gap, the oil layers are present. Okay. Try this, all of you. I'll give you 3 minutes. So the idea here is to imagine the layers sliding, which we have already done. The layer which is in contact with the cylinder is in the shape of a cylinder, okay, hollow cylinder. So the area of contact between the sliding cylinder and the oil, fine, the area of contact becomes 2 pi small r multiplied with L. Okay, only the curved surface of the cylinder is in contact with oil, right? So area of contact is this much. What else do we need for viscous force? Viscous force, the formula is eta A delta V divided by delta Y. See, in that case, we called it Y, that's fine. Basically, it's a separation between layers, okay? Fine. So we got A. We know eta is given in the question. Then the relative speed between two fluid layers, okay? Between two oil layers in this case. Now, whatever is the speed of the cylinder, same will be the speed of the oil layer, which is in contact with the cylinder. So that V. And the last layer, which is in contact with the pipe, tube, will be at rest. So we know that relative speed is V minus 0. So we'll take that as V itself. Speed of cylinder minus speed of the tube. Tube is at rest. So this becomes V itself. And the separation between them. How much is the separation between these two layers? Capital R minus small r. So delta Y becomes capital R minus small r. Therefore, the total viscous force acting on the cylinder as it falls down is eta. Area of contact is 2 pi small r into L. Delta V is V itself divided by delta Y is capital R minus small r. Now, when will the cylinder attain a steady velocity? When its weight is balanced by the viscous force. So this should be equated to mg. How do we write mass? Density into volume. Volume is pi small r square L and then g. That's all. Cancel whatever you can. Pi small r, pi small r. L gets cancelled. Okay, so it does not depend on the length of the cylinder. That's it. Therefore, the terminal speed or the final steady speed with which the cylinder falls is rho r. Okay, one small r is there. G capital R minus small r divided by 2 eta. Mm, Vanilla, where all did you make mistakes?
There I wrote the area of cross section.
Area of cross section you took wrong. Okay, fine, fine, fine. So this is the final speed with which the cylinder falls. Okay, this is a tough question, but questions like this can be asked in JEE. Okay, so let's summarize what all we discussed today. We first discussed about laminar flow. Okay, basically when fluid flows, in the form of layers, we call it as laminar flow. What do you mean by fluid flowing in the form of layers? One set of molecules which is in contact with the surface will have one velocity. Okay, actually zero. The next set of molecules, next layer of molecules will have one common velocity. The third layer will have one common velocity. So layer by layer, the fluid molecules will have common velocity. That is called laminar flow. Okay, different layers can have different velocities, but all particles of a single layer must have the same velocity. We call that as laminar flow, and this can be observed in liquids as well as gases. Viscosity is a property of liquids and gases. Okay, even laminar flow. It's harder to observe in gases, laminar flow, but it can be achieved. Okay. At the macroscopic scale, it's possible. Next, we discuss the no slide condition or the boundary layer condition. The layer of fluid molecules which are in contact with a surface must be at rest with respect to the surface. So if there's water flowing on a surface, the first layer of water molecules which touches that surface should be at rest. The next layer can flow with some speed. The third layer can flow with some more speed. Okay. So relatively between layers, there will be speed. Okay. I gave an example of that also. The first layer is at rest, 0. Let's say the second layer moves on the first layer with a speed of 2 meters per second. Then the second layer speed will be 2 meters per second. Third layer moves on the second layer with a speed 2 meters per second, means its actual velocity becomes 4 meters per second. Third layer's actual velocity becomes 4 meters per second. So that way, as you move away from the surface, layer by layer, the velocity will increase. Okay. Relative velocity between layers will be there. So layer by layer, the velocity will go on increasing as you move from the surface. So we visualize the flow velocity profile. Okay, of layers in a circular tube as well. Next, we talked about viscous force acting on a flat surface. So the formula is eta A delta V by delta Y. Eta is the coefficient of viscosity of the fluid on which the object is moving, or in contact with which the object is moving. A is the area of contact. Delta V is the relative speed between any two fluid layers. Delta Y is the separation between them. We discussed SI unit dimensional formula of coefficient of viscosity and all, then solve the problems. Fine. Tomorrow's class, we will discuss viscous force acting on a spherical object. Okay, it's given by something called Stokes' law. Very easy. We'll discuss that. We'll derive terminal velocity of a spherical object. And after that, one small part will be left, Poisson's equation. Tomorrow we'll finish this chapter. Okay, thank you all. We'll continue tomorrow.